technology. I shared an office with Hujun for many years, and he came down for
8 years.
For a conference. So it was a privilege of him coming by today. And Bram and Gerrit, two PhD students of Hujun, and they've done some amazing work in Eindhoven. They're going to tell you all about it. So, yeah. Please.
Okay. Thank you very much. I think the presentations will take like 1 hour in total. Would that be okay? Or too much?
You can make it shorter, it's better.
Okay. I'll try to make it do the presentation within 1 hour. I will present a kind of overall image of our faculty in industrial design in Eindhoven University of Technology first, and then I will try to briefly talk about my work, related projects, and then Bram will introduce his work, and Gerrit will do a presentation about his work, and I will briefly talk about one of the projects in more details. Okay. Next, I'm going to show a standard movie. But before I start with the movie, as Christoph said, I've been working with Christoph for a lot of years. We are also good friends in the private life. So if you want to know any secrets about Christoph in his professional and private lives, and you can contact me. Next video I'm going to show is a kind of PR video that we try to use this video to attract more students to the design studies. So it gives a kind of overall image, a good overall image about the faculty. So then I don't have to talk, I just sit back and let's watch the video. Okay, that was the faculty. Actually, what makes the industrial design faculty in Eindhoven kind of special from other design studies is that, as you could see from the video, this study is more technical oriented. So what the faculty says, we are training the designers who are going to create intelligent systems, products, and the related services. So it's not traditional industrial design work with only the forms, but more with the behavior also in the products, and also from a system perspective. I've been working in the faculty as assistant professor now for almost 9 years. Should get promoted soon, I guess. I'm not getting stuck there. My background is computer science and human-computer interaction. Actually, I did the same education as Christoph did in Eindhoven in the area of user-system interaction. But I have a more technical influence to my own kind of interest. So what I'm going to next to show you is the projects that other is done by me or I participated. And personally, I'm very much interested in kind of to look at how the physical world is influenced by the digital world that we're creating, and vice versa. So how does it influence the design? When I talk about the digital world and physical world, and I often said there's opportunity for the designers to manipulate the boundary between the digital world and the physical world. And people also often ask, what do you mean by manipulating? There are actually a few aspects we can look at it. We talk about manipulating the boundaries of the physical and digital. One of the ways is to blur it. This is a master project done by master students, in which that the students try to create a kind of digital world which is identical to the physical world. And then in this digital world, there's kind of a virtual creature living in this environment, and children can play with it, interact with it in this environment. Because it's coupled to the physical environment, it requires the children to physically move and interact with the digital objects in this environment. In order to see it, actually to hear it, because in this screen you don't see any display. Use a kind of audio finder, search through the space to talk to or to listen to the digital objects. That is one of the ways to manipulate boundary, just to blur them. So in this application, that's very hard to identify where the boundary is, where the actual interface is. Another way of manipulating the boundary is to augment in both directions the digital world or the physical world. At the left is an example to use physical objects to augment the digital memory, digital pictures. And people can play with the digital memory by playing with the physical object to give kind of physical handle to the digital objects. On your right side is the augmenting physical environment. One of the examples is to actually put the digital information into the physical environment by, for example, digital arts, artistic lighting. Here, example actually couples to a video image which is recorded in real time and shown with the artistic lighting to show the movement, the color composition with distorted form. So if you don't know this coupling, when you step into the environment, what you can see is the only kind of colorful lighting. But if people know this is coupled to a kind of video, people perceive the movement. Sometimes they see color, the color composition of the lighting. They will guess the environment where the video is recorded in time. Mixed realities. I think here we do a lot of augmented reality in HITLab. One of the projects we have done, and also Christoph participated when he was in Eindhoven, is a project called Alice Adventure in Wonderland, where we try to implement the experience of Alice when she traveled into the underground world and encountered a lot of strange things. There she had to go down into a rabbit hole and being in a room, getting bigger and smaller, and try to swim with a rat and this and that. And there we implement the 6 stages of them. We utilize all kind of mixed reality installations. I will show you some pictures later. Connecting physical and digital objects That's actually the topic Bram and Gerrit will talk about later in details, so I just skip this part. Crossing realities, when you fly from one place to another, especially from Europe to New Zealand, it takes a lot of mental effort to actually adjust to everything. How to make this process smoother, especially in a kind of transitional environment like airplane. How to adjust the lighting, how to adjust the entertainment content to reduce the stress, to make people feel more comfortable with the time change and everything else. So this is one of the projects we have done there. Recently, we actually made a kind of flight simulator, a very cheap one. The whole thing is sitting on top of 4 air balloons, which are kind of controlled by using compressed air, so that it can be charged and discharged to simulate the taking off and landing experience. We could also use some big motors to simulate the turbulence, etc. And then we could do certain experiments, actually lock people up in this environment, for example, for 12 hours to simulate the long-haul flight in order to do certain user experience studies. Now, this is a List project. Now we actually have a new PhD student working on it, actually working on software architecture for controlling this kind of environment. In this picture, you could see there all kind of mixed reality. First one is actually a robot, look like a rabbit, but it is a robot sitting on a robotic platform. When Christoph was still working in Eindhoven, this robot was not actually automated. It's all remote controlled.
This remote controlled car with a rabbit put on top.
Yes. And then there's a rabbit hole, and there's a 5-sided cave. And the caterpillar is a robot, but sitting on there, it does not move at all. But the head could change, and only one eye could look at people according to where the sun is from. The treasure cat is actually a projection, a back projection in the dark, in the grass to simulate, or in the trees to simulate the thing. Because it's very hard to simulate the appearing and disappearing of the treasure cat of this cat. So that was a List installation. We are still working on it after Christoph left. We got a new place, and it's very hard to actually set it up again. This is the flight simulator I just explained. We actually went to the a kind of flight airplane junkyard in France to collect all kind of pieces of the airplanes in order to make it, when you enter it, look and feel real. Did you see it when it's working?
I've seen it operate to some degree.
No. And this is actually a vision studio set up by Christoph. After Christoph left, I had to take it over. Now it's handed over to another person, which is actually very a big 7x3x7 screen with front projection, where you can actually do experiments with interaction with big pictures in such a theater. And we recently just graduated one PhD, or 2 PhD students. This is a recent one. I was one of the supervisors, and Christoph is another. Actually, he was one of the PhDs of Christoph, and when Christoph left, I had to take it over because everything Christoph left over, I had to take it over. I had just had to do a lot of work. In this one, is actually this project is about connecting the robots to the digital world to utilize physical robots as embodied in, interface to the virtual world. And the metaverse is actually a European project which tries to come up with protocols to connect different virtual worlds. The protocol is called MPAC-V. They're still working on it. It's not MPAC-5, but MPAC-V. V stands for virtual realities, virtual worlds. And Sophia project is also another European project. It stands for Smart Objects for Intelligent Applications. Sounds very cool. I think Bram will talk about it later in detail, so I just skip this part and you see these two are actually sitting here. Roila, robotic interaction language, one of the PhD students of Christoph that I had to take over. And I think some of you have also involved later to writing up a training material for the Roila language. We took a different approach towards human-robot interaction. Usually, we try to improve the robot to better understand human language. And this is the other way around. We design language for the robot to be easier for the robot to understand, but for people, they have to pay a little bit of effort to learn it. How to design such a language, what would be the consequences to people who are learning it. That was actually the PhD research. If you're interested, I think Christoph has a lot to tell. Talking tangibles, and this is also a PhD project which focuses on the interaction with certain systems, not within your attention space, but in your periphery space. You have to sometimes interact with certain things that you don't want to pay attention to. For example, now I don't know how much time I have spent. Maybe I've spent only 15 minutes. I have to go faster. Now, how do I know this 15 minutes? There's no clock at that side. It could be some kind of design to give you a certain impression. Oh, okay. When did we start? To give you people integration about time, for example, but not in their attention space. Often human-computer interaction requires their attention. How do we utilize periphery information? Not to require people's attention, still to make interaction possible. And this PhD student has left. He didn't finish the project, but the project was quite interesting. Was to make the environment more responsive to people's behavior. It's not for interaction, but it's just to adapt, to make the environment more adaptive. What do you do, how you behave in such an environment. Recently, I moved my research interest towards Internet of Things, and also the combination of Internet of Things and social media. So how do we mix the social media life with the physical life we have normally? One of the approaches is actually to utilize the Internet of Things, put sensors and actuators around in the environment and connect this information, which are actually relate to the human behavior, to social media, in order to share or to either to improve or to share your daily experience. And this is one of the examples that done by master student, is to actually use the doormat to interact with the appliances in the environment when you enter and leave the house. So when you leave the house, you've got to be aware that what are the devices are still on, what are the things still operating, whether it's necessary to switch it off. If it is necessary, then how to switch it off with such a simple device. When you come to the house, you want to switch certain things on quickly. And what are the things already on? For example, when you're into the house, maybe certain device has already been switched on by yourself, remotely use other applications. And this doormat could act as a kind of confirmation when you stand in front of your own door. Okay, the water is in it, the bath is ready, etc., etc. You want to switch on television, then you switch on television, step into the house, everything is ready, just by using such a simple device. And the doormat is a good example of how to embed Internet of Things into our daily life. And how interface is designed. If you are interested, you could search on the internet just for doormat. You will find it. Here is a snap scenario where you enter and leave the house. I'm not going to go into the details. That's part of the information. I skipped this one because it's taking too much time. We also work with a lot of health applications. I'm not very much involved, but still I'm quite involved in some of them, especially for early born babies, how to take care of them when they are still in the incubator, how to make the connection between the baby and parents. What is being done now in the hospitals, they put a lot of electrodes actually stick to the baby's body, which creates a lot of stress to the baby, and this baby later will have problems in development in their later lives. What we try to do is to use the sensors which are interweaved into the baby jackets, for example, into the fabrics, and also to detect certain signal for the doctors and for the parents, but also put certain actuators into the fabrics. For example, for this project it's called Cocoon, to mimic when babies are kind of in a kind of stress. If the mom comes and to hold them, their stress will be reduced, and this jacket just to simulate that kind of behavior. If the stress is detected, and the cocoon or the jacket will shrink a little bit to give the baby a kind of comfortable hug to reduce their stress. Actually, the student got small funding on this project to further develop it. Tangible social networking. So for elderly, it's very hard to use the computers. Now, this one is to actually try to utilize tea boxes, because in Holland people like to drink tea together, especially when they get old. So the student designed a kind of tea box, but still there's one problem with this design, is that you still see the keyboard. The keyboard is hidden inside the tea box if something is different. Actually, the idea was to use the camera which is embedded in the tea box. We want to send a message right on it, kind of post it, put it somewhere, and then the message will be sent. You're doing a lot of augmented reality camera recognition, this and that, you know it can be done. It's quite easy. But certain problem the student could solve, the design students, they could not solve, but put a keyboard in the tea box. A good example of the bad examples. Here is an example that we do it with a master student, is to actually connect your heartbeat to something which is meaningful. This application is actually using heart rate sensor. In the course we use a kind of a clip to your finger. You don't see this picture because it's on the right hand, it's hidden in there. Heart rate will be detected, it will be analyzed. When you read a book, you might get excited, get stressed, etc. And this information will be detected, we show at the corner of the book with colors. Could be kind of interesting for people, because when people are reading the book, they are often isolated in their own stories. In this way, that maybe the family can participate. Okay, now you're getting excited, maybe you need some comfort, get a coffee or something. many of these kind of examples. I think this presentation was done last summer, not really updated. One of the things which I think is interesting and exciting to do in a design faculty is that all the time you're facing new projects, small projects. And one of the problems is that these projects often are isolated. They're not well connected. So if you want to establish a kind of research line, and you want to involve the students, sometimes it's not that easy. Because students have their own interests, and you have your own research interest. You want to attract them to your research interests. It's not that easy. But the good side is that every time you see interesting project. Okay, that was my introduction. I think, Bram, you have to present your work in 5 minutes or so.
I'll speed up. So, maybe a little bit of background. So I'm a PhD student at was not turned on. Okay. So I'm a PhD student at the faculty. I also studied there, so I did both my bachelor's and my master's there. And now already for 3 years a PhD. I think actually today is, or tomorrow is my official last working day. So I'm almost done. I'm graduating this summer, probably, if everything goes well. So yeah, okay. This presentation is part of the PhD work of both Gerrit and I, and we presented some of our work during the conference last week in Wellington. I will try to make it a little bit more general, so I don't have to go in all the details, because that might take a little bit too much time. So the project that we're doing with, well, June already mentioned it very briefly, is about smart environments. And we see these smart environments as kind of ecosystems of objects that connect to the internet or to each other or through the internet to each other. That they can also interoperate, so they can share content, but maybe also share controls. And the objects that we targeted, or the products that we targeted in this project, is both like objects that are already around, like smartphones and these kind of things, but also we tried to focus on developing new objects, and also the rest of the project focused on that. For me personally, I looked also on very specific on the connections and the relations between these objects. So not only the objects themselves, but also the relations that you can make between them and where you can actually do things together. So we kind of then create a way of interacting that is no longer on a single object, but kind of goes across the whole system of objects and products. Very cool name, Smart Objects for Intelligent Applications. The Sophia project, like June mentioned already. I will now kind of cheat a little bit and show you a little movie that nicely introduces the challenges of this project. And it's actually not a movie by the people from the Sophia project, but by a partner project that is building on the outcomes of the Sophia project. See.
People have always found ways to communicate and invent. Now, digital technology is pushing that process forwards, faster than ever before. The gadgets in our pockets are getting smarter and more powerful as microchips get cheaper. In fact, these chips are getting so cheap that we can put them into all sorts of things. Things we hadn't thought of putting chips into before. That means ordinary, everyday items are changing, becoming smarter and connected to the world around them. Since February 2011, AT&T have had more machine subscribers than human ones. That's things like home appliances, car tracking systems, and machines in factories. By 2020, there could be as many as 50 billion smart devices connected to the internet. As these connected devices become more widespread, they can help us keep fit and stay healthy, make our environment safer and more efficient, and use limited resources in the most efficient way. So as people come to rely more on all this interconnected technology, the more we might start seeing frustration and confusion in unexpected places. So what can we do to plan ahead? There are many challenges to overcome. For example, we need to make sure it's easy to connect everything together and keep it working. Most people don't want to become technical experts. As this technology reaches further into our lives, we need to be sure people feel in control of the devices and services around them. Not the other way round. Once these things become interconnected, we need to be able to move between them in a fluid way. We call this interusability. Finally, we need a better understanding of how to design for this interconnected world. The SmartCos project, involving 17 partners from across Europe, has been set up to look for solutions to these challenges. For more information or to get in touch, you can...
So, we're very unhappy that we're not in this anymore. I mean, this follow-up project, because this is where it gets really interesting. But we did some of the preparation work for that. There it is. Yeah. So some of the design challenges that were already mentioned. So we have this increasingly number of wireless connections between all the objects, and we kind of lose track of what is connected to what, and we also we don't really know what is happening anymore. So what we try to do is kind of make this control more physical and more comprehensible, by creating interfaces to the connections, and not only using the objects. And I think one of the main challenges that we face is that this interoperability, as we envision it, is kind of what they call serendipitous interoperability. So these smart objects, they were not really designed to work together, or not let's say as a whole system designed to work together. And yet you want, when you connect them, to kind of create a smooth overall user experience. So what we've defined is a semantic connection, which is a meaningful connection between two objects. So I will just read it to you. A semantic connection is a relationship between two entities in a smart environment and focuses on the semantics or meaning of the connections between these entities. And the way we kind of see it is we have two smart objects in the physical world, and they have a connection. And this connection can be any kind of connection. It can be a wireless, Bluetooth, Wi-Fi, doesn't really matter. And we don't want users to be concerned with this. I mean, if you look nowadays, if you want to exchange information between two phones, you have to kind of see, well, can we use Bluetooth? And what do we have to do to pair? Do we have to negotiate password? And basically what a user wants to do is they just want to move a photo or a music file. So we kind of want them to operate on that level and not be dealing with these nuances of the technicalities. So yeah, we model them by having like all the physical objects kind of also have a digital representation. And although the work that we are presenting now is a little bit focused above the water in the physical world, Gerrit has been working quite a lot on like below the water, let's say the digital domain, how there you can model these connections and also the objects. So we defined an interaction model. It's a little bit complicated maybe to explain everything, but maybe briefly, as users interact with one of the objects that are connected, they kind of, their actions are kind of modeled digitally, and they move across the objects. And what we also made sure is that as they operate on one device, also the types of feedback, or the feedback that they get is also nicely showing up on the connected devices. So they kind of get an idea of how the relationship between these objects are. And we did a lot of testing also with users to see whether they can actually grasp these connections, and we kind of investigated their mental models as they were interacting with them. We also looked at what it means if you make a connection, and kind of if you say, okay, this connection has a directionality, what does it mean for the information that is exchanged and for the user interaction that comes with the connection? And also, what if you connect an object called A to B and B to C, do we also have transitivity, and is that something that users can also still understand? What we draw upon is a theory of product semantics. I don't know if you're familiar with it, but it basically describes how, or is the study of how objects and products can acquire meaning. And we kind of employ these because this is what kind of designers employ to communicate what a product is and what it can do. We kind of draw upon the overlap in meanings of, let's say, two connected objects. So here you see a iPod and a stereo set, and for users, conceptually, these things belong together. I mean, they are in the same product family, they have something to do with meaning, so they kind of expect already something to happen in terms of music exchange when they connect these things. And that's where we kind of see this emergent functionality between the overlap of the two objects. And we also looked at how the feedback and feed forward, which is the information that the user receives before they act, how these things change when you interact with a whole system of interconnected smart objects. And we basically applied a framework called the Frogger framework, which explains and also analyzes how you can use different types of feedback and feed forward to maintain a nice link or a good link between the user actions and the product's functions. Where we kind of treat the inherent and augmented feedback and feed forward as kind of more about the how, and the functional and augmented feedback as what an object can do. And with inherent, augmented, and functional, it kind of it explains where the source of this information comes from. So inherent feedback and feed forward is feedback that comes from the action itself and from the controls itself. So buttons kind of have a inherent feed forward, which is close to the term affordances. So you kind of feel that you can press it, and also inherent feedback means that you get feedback from this control inherently. And augmented feedback just means that it comes from an additional source that is kind of augmented onto the real world. And the functional feedback and feed forward is about the real function of the product. So functional feedback would be, I press the light switch and I see the light go on, something like that. And what we kind of looked into is how these things change when it happens over distributed objects. Maybe this is a little bit too much detail, but what we kind of see is that the inherent feedback and feed forward, they are kind of physical, so they stay where they are with the object that you're currently operating with. But the augmented and functional feedback and feed forward, they kind of are more in the digital world, and they kind of emerge more from the digital world. And So you can also see that these types of information, they kind of travel over the connections. Maybe I stop here and you keep this in mind, and then you watch Gerrit's presentation and you can kind of see how we implemented this.
Okay, hi guys. I'm Gerrit, Niezen. I'm also almost finished with my PhD, but I still have to complete the thesis. So hopefully by the end of June, I will also have a thesis and also be done with my PhD. My background is in computer engineering. I originally studied in South Africa, and I'm also now at the University of Eindhoven. I will try to do my 20-minute presentation in 10 minutes. So I'm going to skip a lot of stuff, but hopefully still get to the essence of the actual presentation. Basically what I want to do is to look at two approaches that we use to see how we could implement this idea of semantic connections, so that you have a very simple way of exploring connections between devices, make these connections, break existing connections, and also how you would then exchange information between the devices on a very high semantic level, so that you don't have to worry about the low-level details, whether you're using a Bluetooth or Wi-Fi implementation. Just the fact that you want to use this device to control that device, or you want to exchange information from this device to that device should be enough. So we looked at two approaches. We looked at both a tangible and an augmented reality approach that I quickly want to discuss with you today. The tangible approach we do with the device that we call the connector object. It is basically a small microcontroller with a RFID module and a small Bluetooth module that is inside the device. It consists of, the one there on the left, that consists of two interlocking modules. And what you can do is you can scan different devices, and when you scan the first device, it shows you on the first inner LED segment whether it recognized the device. You can then walk over to another device and scan that one, and it will either show you whether a connection is possible by flashing a green lighting pattern, or it will show you that there is an existing connection, so it will show a solid green light, or it shows you a red light at the top showing that a connection is not possible. If you have an existing connection, you can actually pull on the two pieces to break the connection, or if the connection is possible, you can push the two pieces together in order to make a connection. So the idea is basically based around the idea of a magnifying glass that you can use to look at devices in the environment, and it allows for a nice exploratory approach to these connections. Here you can see where we're actually scanning a lighting device, and you can see the lights light up on top of the connector object. Then our other approach that we're going to look at, or that we looked at, was the augmented reality approach. And here we use the device called the Spotlight navigation device. And basically what it is a Pico projector that has also a small microcontroller inside. It has and it has an inertial measurement unit or motion sensor inside. So it knows its exact location in space. And what's nice about that is you can actually then point it at a device. And when you point it at a device, it knows its location in space, so it projects an icon of that device right next to the object. And you can then, using a click and drop approach, you can kind of click and drag a line between two devices, and in such a way make a connection. So you can see an example of that happening, where on the left we have a lighting device with the icon of the lamp, and on the right we have a speaker. And you can then kind of click and drag with your Pico projector between them and create a connection. We also use similar semantics, so that a red connection means it's not possible. You can also break connections by shaking the device when you have an existing connection between the two. Okay, so what we did is with the Sophia project, we had quite a number of partners involved that we all had this experimental setup together. So all these devices are from different companies and different manufacturers. So kind of we kind of tested it to show both that the software architecture that we developed works to allow devices from different manufacturers to communicate with one another. But also my focus was more on how you would go about describing the capabilities of these devices using ontologies and other semantic web technologies. And well, I'll show you a quick video to explain the setup of all the different devices.
As part of the SOFIA project, funded by the European Artemis program, a smart home pilot was conducted at the Experience Lab of Philips Research in Eindhoven in the Netherlands. 21 participants were recruited for a user study and were presented with the following scenario. When SOFIA enters the room, is detected and the functional lighting turns on. SOFIA selects a book from her bookcase and sits down to read, wondering what her two friends, Mark and Dries, are up to. The wall wash lighting in the house of Mark and Dries also turn on when they enter their living room. Sensors on the wall update the semantic information broker with presence information, and the wall wash lighting, being subscribed to these kinds of events, responds when their presence is detected. Mark takes out his mobile phone to play a song for Dries. While they are listening to the music, Mark explains to Dries that the music player can be connected to the lighting device in the room to render the mood of the music. This is achieved using the white connector object lying on the table. There is a tag on the mobile phone that Dries scans using the connector object. 4 light segments on the object turn on in sequence, indicating that the mobile phone is recognized. Dries walks over to the lighting device and holds it up to its tag, where a second light sequence lights up. The light segments flash green, indicating that a connection is possible, and Dries presses the connector object to make the connection. The lighting device renders a lighting pattern based on the music. Back at her place, SOFIA notices that Mark and Dries are listening to music, as the same lighting pattern is rendered on her lighting device as well. She would like to know what music they are listening to, and picks up her spotlight navigation device. As she picks it up, the functional lighting in the room dims down to allow the spotlight navigation to project an image on the wall. Using an augmented reality approach, the light in the sound system is visualized, and she draws a connection between the two using the spotlight navigation device. The same music that is playing at Mark and Dries is now also playing on her sound system. Since users are directly in control of the connections between the objects, Mark and Dries can also break the connection between the mobile phone and the lighting device. Mark scans the phone's tag again using the connector object and waits for the light sequence to complete. He then goes back to the lighting device and scans the other tag. A solid green light indicates that the devices are connected. He then pulls the connector object, breaking the connection between the two devices. The wall wash lighting in the room turns back on.
Okay, so basically we had 2 separate locations set up within the Experience Lab. Downstairs we were testing the tangible approach, and on the left we had the upstairs setup which we used to test the augmented reality approach. And there you can see all the devices, including the permanent and the temporary connections that we used in the setup. Okay, so we performed an evaluation during a week that this setup was running in the Experience Lab. It had 21 participants of average age of around 28 and a half. 9 were living alone, 11 cohabiting, and they reported their self-familiarity score with interactive systems as 6 on a scale of 1 to 7. So what we did was we basically looked at how could we elicit their mental models, how we could figure out how they experience the system and how they see it, how it connects to how all the devices connect to each other. So we recorded these mental models using the teach-back protocol, which means we looked at both the semantic knowledge or the what is questions, as well as the procedural knowledge or the how-to questions. And basically what we did is when they would arrive, we would give them a predefined list of tasks which they had to accomplish while within the room, and then thinking out loud while they do each task. Once they complete the list of tasks, they could then still kind of explore the system and make sure that all their assumptions are correct with regards to how the system works. And then they had an interview afterwards. So we would first have them draw down their mental model and explain how they think the system fits together, and then also have an interview with a number of questions. These are some of the results where you can see the mental models that some of the users drew. You can see here, there is the connector object over there, and it's basically seen as a part of the system. So it's really just, from the user's point of view, another smart object in the system. It is connected to all the other devices, but they don't see it as a special separate device. It's just another device in the system. You can also see that here there's a question mark above the sensor, where in any case where there was something that happened automatically, so that it was an incidental interaction instead of an intentional interaction that the user made, they had much more trouble to visualize how this would fit in together with the rest of the system. Here's another example of a mental model where you can see this user had a very strong spatial layout of the system, so that even though the TV there wasn't part of the system, they still drew it and showed the lighting device next to it, just because that is where it was located. Okay, so what we did was we looked at a few concepts while evaluating the mental models. So we first looked at completeness. Did the users see all the different devices, and did they also correctly recognize all the connections between the devices? And in most of the cases, it was not a problem in the case where there was intentional interaction. But in the cases where there were incidental interactions, so things happening automatically, there were some things missing in the mental models where they clearly did not understand what was happening. We also evaluated the semantic connections or the user's concepts of these semantic connections themselves. We looked at things like directionality. Even though there wasn't a concept of directionality in the system itself, users still had a very strong feeling of, when I connect this object to that object, it means that I want to transfer information from this device to that device. So they had the strong feeling of directionality while making these connections. Also transitivity, when you have one device that's connected to a second device, and that second device is connected to a third device, performing an action on the first device and having an effect on the third device would be perfectly normal, even though the first and the third one is not directly connected. This concept of transitivity did not pose a problem for the users. Also priority, even though in our system we did not really have a problem or a case where you would have to distinguish between priority between two devices, users immediately thought that, well, they already started thinking of, how can I solve this problem if I have two devices that are connected to a third device, which one should have priority? And they also clearly distinguish between temporary and persistent connections, where some things would always be connected, or some things like a friend visiting and their mobile phone being connected to your system, that should only be temporary. When the user leaves and comes back at a later time, that connections shouldn't persist. We also looked at the organizational layout. So basically most of the people had a spatial layout when they drew these mental models. There were two users that actually had a more logical network layout approach. We were assuming they were the engineers that took part. And then for the network structure, we looked at both. There were both concepts of star networks being drawn, where everything would be connected to a central object, and other users would have a more peer-to-peer approach, where each device would be connected to another device. And we even had some hybrid structures as well, where they would combine both star networks and peer-to-peer networks. Okay, so to conclude, basically, most of the users reported that they experienced this as being a very simple way of making connections between devices, and they actually felt that they wanted to be able to connect more devices in the room, and we didn't instrument those, so they were a bit frustrated that they could only make connections between some of the devices in the environment. Then, as I showed earlier in the mental model, they clearly saw the connector object as being a part of the system. Also as a way of kind of carrying content between objects. So you could kind of take music from the mobile phone and take it to the speaker and drop it on the speaker. So this connector object was a way of carrying content. Whereas the Spotlight navigation was really seen as something that's out of the system. It was kind of seen as a remote control where you can use it to make connections between objects, but it was never seen as a part of the system itself. And then, yeah, I've already explained the difference between intentional versus incidental interaction, where in the case of incidental interaction, it proved a lot more problematic for the user's mental models. Yeah, that's about it. Thank you.
Maybe you guys have questions for us?
I heard you mention briefly about MP3 before. Is the later project you've mentioned about connecting smart objects also part of MP3 standard, or
The work that Bram and Gerrit just presented is not related to the MP3 protocol. Previous PhD student, Christoph, is also a supervisor for him. He did some work for MP3, where it's actually about the protocol connecting different virtual worlds. Our position in that project was to contribute from the perspectives of how to connect the physical world to the physical world, to the virtual world. How to make the connection, how to interface. One of the approaches that we use is embedded interaction, especially using robot, for connecting virtual worlds and the physical world.
So when you want to connect physical devices, there should be certainly a kind of connection which is below the surface, which connects between the digital devices. What kind of protocol or what kind of?
Okay, so within the Sophia project, there was a protocol developed called the Smart Space Access Protocol. And basically what it allows you to do is to share information with a information broker in triple format. And you could also then subscribe to changes of these triples, as well as insert and remove information. And that runs on top of a TCP/IP network. So that's kind of how interoperability is achieved. That we assume all the devices to be available on a TCP/IP network, and then use SSAP to communicate with one another.
So it's basically all devices connected to the internet.
To a central information broker, yeah. And that is also then a triple store. So the focus of my PhD work is to take the information on this triple store and figure out how it should be stored. Also, how you would store information about the capabilities of the smart objects themselves. And then we use a reasoner, and we use reasoning technology to kind of figure out if we have triples coming from different devices, how we can figure out how they can be connected to each other.
Actually, the back end of technology of the Sophia project is actually the same technology used for Siri, for the speech recognition of iPhone. It's based on this semantic technology, semantic web technology. I don't know whether you guys work on semantic web technologies.
I was wondering, you can substitute a connected object in Spotlight navigation on one part of the system, outside the system. One way feel about like something that's sort of in between here, because the Spotlight thing, I guess they had projections on the walls, and you're connecting the projections. It seemed like could be kind of tricky to do. And if you had, let's say, the remote pointing at the object and connecting to the other object directly rather than projections on the wall, would that be something that will potentially sit between the two, because you're kind of connecting, you know what I mean, directly between an object and another object with a remote rather than physically, you know. So the most primitive one, well, the most I I guess, tangible would be take a physical object, like a connector, go to one, you wait, go to the other one, you wait, and you feel like you're part of the system, right? And the most remote one, you're actually taking, I guess, projection of those things on the wall and doing that indirectly, right? And I was thinking something that's in between where you're kind of doing it directly, but you're doing it remotely. Or so you take a remote and maybe it has an object recognition thing from, I don't know, some kind of 3D model, blah, blah, do that. And then it's kind of somewhere between walking up to it and doing that indirect thing on the wall. And I was wondering whether that'll sit between those two extremes and whether that's something
well, originally with the Spotlight navigation device, that was the idea to have it kind of pointing it directly at the devices. It was more just limitations of the technology that we used at the time to especially since we had real users that had to play with these things. We wanted to make sure that we had a clear idea of where something could be connected to something else. It was just easier to project it against the wall. But the idea would be to actually point it at the device itself. We did explore a few other approaches as well. The other slide that Bram had up earlier showed our interaction tile. Maybe, I don't know if it...
Maybe show the last presentation. Yeah, maybe it's also in my presentation.
Right, sure. Yeah, okay, there we have it. So basically we have there on the left the interaction tile. So we kind of had these cubes as proxies for the devices, which you can then place them next to the tile, and it will show you on the light segments whether they can be connected. And then you can kind of shake the tile to make it or break a connection. And then we have this one here in the middle as well, where the cubes themselves can be placed next to each other to show which devices should be connected to one another. But yeah, of course, this one also separates the devices from these proxy objects, so it makes it also a little bit more difficult to comprehend.
Thank you very much for your time.
Thank you for listening, and we managed within